Somewhere in the frozen south of another world, something is carving thousands of black scars into the ground, and for 21 years no human being could explain how. They call them spiders, not because anything is alive down there, because that is the only word the human mind could reach for when it first saw the shape. Branching, radiating, hundreds of jagged legs clawing outward from a central point, spreading for over a kilometer across the frozen dust of the Martian South Pole. Seen from orbit, entire regions of Mars look infested, as if some vast, dark network had crawled up from beneath the crust and frozen mid-motion. This is not science fiction. This is not a hoax. It's a real geological feature on a real planet. It's photographed again and again by real spacecraft, and for 2 decades, it sat there in the data, defying explanation. Somewhere between the questions, how did this form, and what does this mean for the planet next door, an entire chapter of planetary science was quietly being rewritten. And the strangest part of the story isn't the pattern itself. It's what it took to finally understand it, and what still, even now, remains unresolved. To understand why these shapes terrified and fascinated scientists in equal measure, you have to go back to the moment they were first seen. In 2003, images beamed back from spacecraft orbiting Mars revealed something that did not belong to any known category of terrain. Not craters, not lava flows, not dunes. Something new, branching, dark, spidery marks fanning out across the southern polar plains in their thousands, appearing and vanishing with the seasons like something breathing beneath the surface. Scientists gave them a clinical name: Araneoform terrain, from the Latin for spider-shaped. But the nickname that stuck Mars spiders captured something the technical term never could: a primal unease, sense that this alien world was doing something none of us fully understood. Right in front of the cameras, on a schedule of its own. Picture the scene from orbit. A camera drifting 250 kilometers above the rust-colored curve of the planet, scanning a landscape locked in permanent winter. Then, emerging from the frost like ink bleeding through parchment, the pattern appears: dark branching scars, sometimes solitary, sometimes clustered into sprawling colonies that stretch for miles, giving the Martian surface the unmistakable texture of something crawling. The first question every scientist asked was the most obvious one. Is this alive? It wasn't. Nothing about. Mars's current environment could sustain biology capable of carving kilometer-wide structures into solid ground. But ruling out life didn't make the mystery smaller. It made it stranger. Because if nothing was alive down there, then some purely physical process, some combination of temperature, pressure, chemistry, and geology, unlike anything on Earth, was doing something no process on our own planet does. And for years, nobody could prove exactly what that process was. This is where the story becomes less about spiders and more about something bigger. How do you solve a mystery on a planet you cannot touch, using only light reflected off 100 million miles of empty space? The leading suspect, almost from the beginning, was carbon dioxide. Mars's atmosphere is almost entirely made of it. Thin, cold, and prone to a seasonal transformation with no real Earth equivalent. Each Martian winter, temperatures at the South Pole plunge low enough that atmospheric carbon dioxide gas doesn't just cool, it skips the liquid phase entirely and freezes directly into solid ice, blanketing the polar terrain in a translucent slab. Then spring arrives, sunlight returns, and something extraordinary happens beneath that ice sheet. Something a geophysicist named Hugh Kiefer began trying to model mathematically in the early 2000s, working from nothing but orbital images and the laws of physics. Kiefer's idea, refined across a series of papers through that decade, became known as the Kiefer model, and it proposed something almost poetic. The layer of carbon dioxide ice, he suggested, behaves like a pane of glass in miniature greenhouse. Sunlight passes straight through the translucent ice and strikes the dark, dust-covered ground underneath. That ground absorbs the light and warms. But the heat has nowhere to go, trapped beneath a lid of frozen gas. As the temperature rises at the base of the ice sheet, the solid carbon dioxide there begins to sublimate. Turning directly into gas without ever becoming liquid, pressure builds and builds. until the ice above simply cannot contain it anymore. Then it cracks. Gas erupts upward through the fracture, carrying with it a plume of dark sand and dust from beneath the ice, spraying it out across the frozen white surface like ink through a fracture in glass. As the pressure searches for the path of least resistance, it doesn't erupt. In one place it branches, carving multiple channels beneath the ice sheet as it searches for weak points, venting again and again along the way. When the ice fully melts away in the Martian summer, what's left behind is the scar of that violent, silent eruption, a dark, branching network etched permanently into the ground below. A spider. It was an elegant theory, mathematically consistent, matched the seasonal timing perfectly, matched the branching geometry. And for nearly 2 decades, it remained exactly that, a theory. Nobody had ever watched it happen. Nobody had proof. Because here is the problem that made this one of the strangest unsolved cases in modern planetary science. Nobody could go and check. Mars sits, on average, over 200 million kilometers from Earth. No rover has ever driven to the spider fields. They lie in some of the most extreme, least accessible terrain on the planet. Regions so cold and so seasonally hostile that even Mars's most advanced robotic explorers have never been sent there. Every spacecraft that has ever photographed a Mars spider photographed it, from orbit, capturing only the beginning state and the end state ice sheet. Then scarred ground, with the entire violent process hidden from view. Buried under meters of frozen gas, unfolding across a Martian spring that no human eye had ever witnessed directly. For 21 years, the Kiefer model was Mars's best guess. Not confirmed, not disproven, just unwitnessed. A working theory holding the weight of an entire class of alien geology, resting on inference rather than observation. And then, in a laboratory just outside Los Angeles, NASA's Jet Propulsion Laboratory decided to do something almost stubbornly simple. If nobody could travel to Mars to watch the spiders form, they would bring Mars to Earth instead. The experiment was led by planetary scientist Lauren McEwen, working with a research team determined to recreate, as precisely as any laboratory on Earth possibly could, the exact physical conditions of the Martian South Pole in spring. That meant building an environment where atmospheric pressure sat at a fraction of what we breathe, where temperatures plunged to the punishing cold of the Martian pole, where a slab of genuine carbon dioxide ice could be layered directly over simulated Martian regolith, a soil substitute engineered to match the mineral composition of the red planet's dust as closely as science allows. Inside a specialized chamber at JPL nicknamed Dusty, built specifically for simulating alien planetary surfaces, the team assembled their miniature Mars. Then they did something no one had ever done in the 21-year history of this mystery. They shined simulated sunlight down onto the ice, and they waited to see if a Martian landscape, shrunk down to the size of a laboratory dish, would do what Hugh Kiefer had predicted on paper 20 years earlier. The ice began to warm. Exactly as the model predicted, began building beneath the surface, invisible, silent, patient. Then it cracked. Gas erupted upward through the fracture in a sudden violent plume, carrying a spray of dark simulated Martian soil up through the ice. And across the surface, and in that instant, decades of theory became witness fact. The lab team, according to the researchers' own account, did not respond with quiet scientific composure. They shouted. One evening, working late, the noise from the lab was loud enough that a lab manager burst through the door thinking there had been an accident, only to find a team of scientists staring stunned at Mars replicated on a tabletop, finally showing them its secret. The findings were published in September 2024 in the Planetary Science Journal, and they did more than confirm Kiefer's model was broadly correct. They revealed something even the original theory hadn't fully anticipated, a hidden second stage. Buried inside the process? As the team studied their miniature Martian landscape more closely, they found that ice wasn't only forming as a sheet on top of the ground. It was also forming within the soil itself, mixing directly into the frozen regolith beneath the surface. And when that subsurface ice began to crack alongside the ice sheet above it, the two fracture systems interacted, shaping the final branching pattern in ways the original model had never accounted for. 21 years of mystery answered and deepened in a chamber the size of a small room. 300 million kilometers from the place it was trying to explain. This is where most documentaries would stop. Mystery solved. Case closed. Roll credits. But that would be the wrong ending, because solving how the spiders form only opens a larger, far more important question. What does it actually tell us? Because these are not just strange shapes. They are a live, active record of a process still happening on Mars today. Right now, every single Martian spring, in a region of the planet almost no spacecraft has ever closely examined. Each spider is a fossil of violence. A frozen signature of gas escaping from beneath the surface with enough force to blast dust and sand through solid ice. And the fact that this happens on a planetary scale, across thousands of individual formations, tells scientists something profound about how dynamic Mars's polar climate still is, even on a world most people imagine as a dead, static desert. Understanding exactly how and where these formations occur has become more than academic curiosity. It has become a tool. Researchers now use the density, shape, and distribution of areniform terrain as a kind of natural instrument, a way of measuring how Mars's seasonal carbon dioxide cycle is behaving year after year, region after region. Some scientists are even applying artificial intelligence to scan through the enormous archive of orbital images, automatically cataloging spider formations across the planet to track subtle shifts in where and how intensely they occur, a possible window into how Mars's climate is evolving, one buried plume of gas at a time. And there is a reason this matters far beyond pure curiosity. Because the process driving these spiders, sunlight penetrating ice, warming a surface below, building pressure, and erupting outward, is not unique to Mars. It is a mechanism, a category of geological behavior that scientists now believe may exist in different forms on other icy worlds scattered across the outer solar system. Worlds where similar ice-driven eruptions might not just move dust, they might be capable of venting material from oceans hidden far beneath frozen crusts, training scientists to look for a signature that could one day matter on a world where the stakes are much higher than dust patterns in a Martian winter. Scientists studying the historical record of past El Niño events have identified a critical distinction between moderate and severe cycles, one that has nothing to do with how the event feels within the Pacific Basin itself, and everything to do with how far its influence travels outward. Moderate El Niño events, like those that developed in 2018, and visible effects primarily within and immediately around the tropical Pacific region, meaningful, but geographically contained. The severe 2015 to 2016 El Niño told a very different story. That event's influence reached far beyond the Pacific entirely, contributing to drought conditions across parts of Africa while simultaneously driving heavy, damaging flooding across California on the opposite side of an entire ocean. Evidence of just how far a sufficiently powerful disruption in one part of the climate system can ripple outward into completely unrelated regions of the globe. There is a deeper, more uncomfortable layer to this story, one that climate researchers have been increasingly vocal about in recent years, because El Niño events no longer occur in isolation from the broader trajectory of a warming planet. They occur on top of it. Researchers studying the previous major El Niño, which developed in 2024, documented something alarming in the Amazon rainforest. During that event, a combination of the natural El Niño-driven dry conditions, layered warming, together drying out vast stretches of the rainforest severely enough to displace communities and devastate local livelihoods. More troubling still, researchers found evidence that some sections of the Amazon, during that stress, flipped from functioning as a net absorber of atmospheric carbon dioxide into becoming a net source of it instead, a phenomenon scientists describe as a regime shift. A moment where an ecosystem crosses a threshold and begins behaving in a fundamentally different way than it did before, potentially for a sustained period afterward, not simply reverting back once the immediate trigger passes. That is the quiet, unsettling undercurrent running beneath every headline about a new El Niño event. It is not just a temporary disruption superimposed on an otherwise stable climate system. Each time one of these events arrives on top of an already warming, this is precisely why the ability to detect a Kelvin wave forming in the western Pacific months before its effects reach the coast of South America has become one of the most quietly consequential capabilities in modern climate science. It transforms preparation from guesswork into something approaching genuine foresight. Coastal communities, agricultural regions, and water resource managers watching an approaching El Niño don't have to simply wait for the rains to shift or fail before responding. Satellite data streaming down from missions like Sentinel-6 gives forecasters, and by extension the communities depending on their forecasts, a multi-month head start to prepare for what's coming, whether that means bracing for flooding in one region or preparing for drought in another, sometimes both occurring at once on opposite sides of the same warming ocean. And the story doesn't end with rainfall and drought. The consequences of a strengthening El Niño reach into corners of the climate system easy to overlook entirely. Fisheries disrupted as warm water displaces the nutrient-rich currents that support marine food webs off the coast of South America, echoing almost exactly the same collapse those 17th-century fishermen first noticed and named centuries ago. Shifts in Atlantic hurricane activity. As the altered wind patterns associated with El Niño tend to suppress hurricane formation in one ocean basin while simultaneously encouraging it in another, and a well-documented statistical relationship between strong El Niño years and elevated global average temperatures, meaning a sufficiently powerful event developing through the back half of 2026 could meaningfully influence whether this year, or the one immediately following it, sets new global temperature records. There is something almost poetic, and more than a little humbling, buried inside the technical achievement that made all of this visible in the first place. A satellite, sitting in orbit, measuring nothing more exotic than the height of the ocean's surface, to a precision finer than the width of a hand, and from that single, deceptively simple measurement, extracting a warning about droughts in Africa, floods in California, disrupted fisheries off Peru, and the fate of carbon stored in the Amazon rainforest, months before any of those consequences actually arrive. The wave detected in the spring of 2026 is still traveling, still building, still being watched, day by day, by a satellite named after a scientist who spent his career advocating for exactly this kind of long-term, unglamorous, quietly essential Earth observation. Sometime between November and January, the accumulated warmth now sliding across the equatorial Pacific will reach its peak, and only then will scientists know with certainty whether 2026 becomes another entry in the historical record beside 1997 and 2015, or something the planet has never quite experienced before. Either way, one truth is now impossible to ignore, sitting in the satellite data for anyone willing to look. The ocean is not a passive backdrop to human civilization, is an active, breathing, physically shifting system, capable of storing enough heat to alter weather patterns on the opposite side of the Earth. And for the first time in human history, we are finally watching it happen in real time, months before the rest of the world will feel it arrive.